Hello everyone. Today we practice the state space design based on the pole replacement method. We consider a second order system showing here. The goal is to design a full state feedback controller with both poles at -2. Firstly, we shall check the controllability of these systems. We write the controllability matrix is equal to BAB for second order systems. Using the matrix calculations, AB is equal to -1 times 0 and -4 -3, and then the control matrix become -1, 2, and -1, -7. And then we can calculate the determinant of this matrix is equal to 7 plus 2 is equal to 9, which is a constant. So we can see the system is controllable. And then we can design the controller with several methods. Here we imply a method called the direct determinant of the vector key. So we design the gain vector equal to k1, k2. And this method can be used when the order of the system less than 3. The eigenvalues of the matrix A minus BK are called the regulated poles. If these poles are placed in the left half S-plane, from the Nyquist diagram, we can say that the system is stable. And if the system the order of the system is bigger than 3, this method can be complex. And so we consider a second order system here. We can write the k equal to k1, k2. And we substitute this k matrix into the desired characteristic polynomials. We can write and equate it with s minus p1, s minus p2, and we let these two equations have the same volumes. Since both sides of these equations are polynomials in S, and by equating the coefficients of the like powers of S on both sides, it is possible to determine the volume of K1 and K2. And the closed loop control systems is equal to A minus BK, which can be write is 1, 0, 3, -2, minus k1 and minus k2, 2k1, 2k2, and it equal to 1 plus k1, k2, 3 minus 2k1 minus 2 minus 2k2. And we can write the Si minus A plus B key equal to determinant Si plus minus A plus B key, and it's equal to S minus A and plus B key minus K1. It's here and here. And then we can write minus K2 here, and then is minus 3 plus 2k1, and then it's minus S minus 2 plus 2k2, which is S plus 2. And it's equal to S minus 1 minus k1 times S minus 2 plus k2. Sorry, plus 2. And minus k2 minus 3 plus 2k1. And we need to solve this equation. We write it as a second order equations as minus 1 plus k1 times S plus 2 plus 2k2 plus k2 minus 3 plus 2k1. And then we calculate the equation as square plus 2 plus 2k2 as minus 1 plus k1 as and minus 1 plus k1 times 2 plus 2k2 and plus 2k1 k2 minus 3k2. When we write I square plus 2 times k2 2k2 minus 1 minus k1 s and minus 2 plus 2k2 plus 2k1 plus 2k1 k2 and plus 2k1 k2 minus 3k2. Then it equal to S square plus minus k1 plus 2k2 plus 1 s minus 2 minus 2k2 minus 2k1 minus 2k1k2 plus 2k1k2 minus 3k2. It equal to s square plus minus k1 plus 2k2 plus 1s plus we animated the k1 k2 plus minus 2 minus 2k1 minus 5k2 and the characteristic equation of the closed loop system can be written based on the defined new poles P1 equal to minus 2, P2 equals minus 2. And we can write s minus 2 square is equal to s plus square plus minus k1 plus k2 2k2 plus 1 s plus minus 2 minus 2k1 minus 5k2 and this 1 equal to s plus 4s plus 4 is equal to and now we got the equations second and third terms. The coefficients should be same. Then we can write minus minus k1 plus 2k2 plus 1 is equal to 4 and minus 2 minus 2k1 minus 5k2 equal to 4. And then we need to solve these equations. We can write minus k1 equal to 4 minus 2k2 minus 1. We substitute minus k1 into the equation 2. We got minus 2 minus 2 k1 is k1 equal to minus 4 plus 2k2 plus 1 minus 5k2 equal to 4. Minus 2 plus 8 minus 4k2 minus 2 minus 5k2 equal to 4 minus 9k2 equal to minus 4 plus 4 equal to 0 and k2 equal to 0 and then k1 equal to minus 3. So the gain matrix is in k equal to -3, 0. And then we solve these examples. Now we solve another example. Design a state feedback controller for the system below such that the stable poles are left in place while the unstable poles are mirrored on the imaginary axis. Now we first solve the original poles of the system. The matrix of the system is below. The poles of the original system are calculated from the matrix A. Is +1 minus -1 is, and it's equal to s squared plus s minus 20. And the poles of the original system can be written as P1 equal to 4, P2 equal to -5 from this equation. And we ask the P1 equal to 4, we mirrored these poles to the left plane. So the desired poles is equal to -4, -5. And we define the desired state feedback in vector k as k equal to k1, k2. And then the closed loop controlled system can be written as A minus BK equal to -1, 20, 1, 2 minus K1, K2, 0 is equal to -1 minus K1, 20 minus K2, 1, 0. And then the characteristic equation of the closed loop system can be written here. K1 and K2 minus 20 minus 1, nice, is equal to S squared plus K1 plus 1 S plus K2 minus 20, and the characteristic equation of the desired systems can be written based on the defined new poles, that is S minus minus 4 times s minus 5. That's equal to s squared plus 9s plus 20. And then we let the coefficients of the two equations equal, and then we can write k1 plus 1 is equal to 9, and k2 minus 20 is equal to 20, so we got k1 equal to 8 and k2 equal to 40, and we solve this problem.